Hi everybody, my name is Greg Hancock, and along with my variance-inflated friend Patrick Curran, we make up Quantitude. We're a podcast dedicated to all things quantitative, ranging from the relevant to the completely irrelevant. In today's episode, we talk about the terrifying, the feared, the dreaded multicollinearity. Blamed for a multitude of general linear model problems, we dare to ask the question, but should it be? Along the way, we also mention having your stump ground out, Fall Guys, Kaiser Soze, croissants and breadsticks, baguettes in space, mostly dead, the Cliffs of Moher, enablers, dangling on a wing and a prayer, nanotech R-squareds, opening a suitcase, reinventing factor analysis, and whiny-ass babies. We hope you enjoyed today's episode. Okay, for the record, you gave me crap last season about being late. You, my friend, are late today.
When I said that I'm going to be late getting on because I am having my stump ground out, it is because I'm having my stump ground out. I had a tree removed from the front yard. They sent this big grinder, and that is exactly what is happening. Nothing else.
Okay, when you said it before, I'm having my stump ground out, I didn't know if that was a euphemism for something. But okay, you literally mean it's yard guys.
Yes. I apologize for being late because I was in my front yard watching my stump be ground out.
Okay, listeners don't necessarily know this, but we wind up blaming yard guys for a lot of stuff, right? I mean, there have been times when we had to just stop recording because I don't know if it's your neighbor Frank who's mowing his lawn outside the window or there's something going on. But yard guys have been to blame for so much lost podcast time.
But isn't that a human universal? We all need a fall guy, and that's gender neutral. Everyone out there, somewhere in your life, you've got a scapegoat, a fall guy, an emotional lightning rod, something that you can go to that this can't possibly be your fault. And for us, you can put it on the yard guy.
This reminds me of a movie where there's this lurking presence out there that gets blamed for absolutely everything, but it is deeply feared. So read my mind. This might be a long shot for you.
I know who you're talking about.
Do you? Okay.
Kaiser Soze.
Yes! Yes! Kaiser Soze.
Who's Kaiser Soze?
Okay, folks, this is one of the best movies.
Yeah.
It's The Usual Suspects. It's out of the 90s. If you're looking for something kind of retro to watch, it is a really wonderful movie. There's a crime, there are drug lords. We won't give it away because it's one of the best 5 minutes at the end of any movie.
Yep.
The cops are trying to figure it out, and the usual suspects are this group of guys who are all criminals that they bring in. And it's all blamed on this mythical drug lord who nobody knows who it is, where he is, whether he's still alive or not. But it's all Kaiser Soze.
The only thing that scares me is Kaiser Soze.
That is just a great movie. Highly, highly recommend for people out there who haven't seen it.
Now, given the alleged focus of this podcast, I will bounce it back to you.
Okay.
Who is the Kaiser Soze of statistics? Sorry, Greg was drinking when I said that. And I wish we had a video recording of this. He almost honked something through his nose.
Okay.
So that was just an added advantage on my part.
You're welcome. All right, so the Kaiser Soze of statistics, the lurking presence that we blame for anything that may or may not actually be responsible for it. Is that what you're asking about?
Exactly. Let me give you a couple of examples.
Okay.
We all see this all the time. Power.
Oh, yeah.
We didn't find an effect. It's because we didn't have sufficient power. Another one I commonly see is we weren't able to differentiate the two groups because we didn't follow them long enough in time.
Oh, yeah.
Had we collected data for another year, the treatment would have been spectacularly effective.
Okay, those are okay.
I'm sorry, okay? Do you have a true Kaiser Soze?
Nobody ever believed he was real. Nobody ever knew him or saw anybody that ever worked directly for him. Anybody could have worked for Soze. You never knew. That was his power.
Well, have one that's better than your power and you're following the groups for longer. Here it is. All right, you ready? See what you think. Multicollinearity.
Done and done.
Okay.
There is nothing in our field that we encounter something we don't like and we blame multicollinearity. Multicollinearity is the Kaiser Soze of statistics.
I'm telling you, it's Kaiser Soze!
Okay, so let's puzzle through it.
Okay.
What exactly is it? Because a lot of times it's used very loosely and oftentimes inappropriately. So what is it? What happens if it exists? What are the downstream costs? How do we identify it? And then should we be treating this as Kaiser Soze, or is there something there that's legitimate?
The greatest trick the devil ever pulled was convincing the world he didn't exist.
How do you want to start things off?
You are a good teacher, my friend. I just want to let you know, I think you're a terrific teacher. Why don't you start us off with the way you think about it from a visual perspective? And if I have anything to add, I will.
First, thank you for the kind words. You're only saying that because you did the shout out on Twitter for identify your teacher. And my ex-student, who we've talked to on the podcast about propensity scores, Noah Griefer, posted that he thought I was an excellent teacher only because nobody had said my name and he didn't want me to feel bad. I laughed out loud when I saw
That
that.
was so sweet of Noah.
It was so sweet.
Yeah.
Okay, very briefly, folks. Everything we do in statistics is multivariate. Everything. All right. If you have more than one variable, it's multivariate. Go ahead and call it bivariate if you have two. It's still multivariate because it's more than one. And we often work with correlation matrices, covariance matrices, and build out from there. Imagine you have two variables. You're looking at predictors of reading ability, you're looking at alcohol use, you're looking at symptomatology, it doesn't matter. And let's call one X and one Y. And we're going to talk about multiple regression mostly here, but it scales up to anything into the general linear model, the SEM factor analysis. It all relates downstream. So imagine that you have one predictor and one outcome, an X and a Y. And we're going to represent those in a Venn diagram. X is going to have a unit variance in a circle. Y is going to have a unit variance in a circle. And the correlation between the two are the degree of overlap between X and Y. So imagine that X and Y are correlated just a little bit. Well, maybe you have a correlation of 0.1 and just those two circles barely overlap. And then they correlate a little bit more and they overlap more and they correlate a lot. And maybe you have a correlation of 0.7 and almost half the circles overlap. That's a bivariate correlation in a Venn diagram. So bring in a second X. All right, so we got X1 and we got X2. Now, cut me some slack here as I'm going to give an unrealistic example that happens in true experimental designs often, but rarely, if ever, in the world that we live in the social behavioral health ed sciences. We're going to have two X's and a Y. The X1 is going to correlate with Y and overlap. And X2 is going to correlate with Y, and that's going to overlap. But in this unrealistic situation, X1 and X2 do not correlate with each other. So X1 and X2 don't overlap themselves. So X1 and XY overlap, X2 and Y overlap, but X1 does not overlap with X2. So what that means is, if you have information about X1, it tells you nothing about X2. If you have information about X2, it tells you nothing about X1. All right, now let's move to reality. And X1 overlaps with Y and X2 overlaps with Y. But now X1 also overlaps with X2. Because having information about depression in an adolescent tells you a little bit about information on anxiety in an adolescent because they correlate. This is where the game gets fun because we have the bivariate relation between X1 and Y ignoring X2. But we also have to now factor in the relation between X1 and Y above and beyond X2, or controlling for X2, because X1 and X2 are correlated. And this is the foundation of multiple regression. We get an overall estimate of the optimal linear combination of our set of predictors in the prediction of our outcome Y, and that's numerically captured in our multiple R squared. But we also, for each predictor, get a regression coefficient, which is the unique effect of each predictor above and beyond the influence of the other predictors. So looking for that part of X1 that overlaps with Y, but does not overlap with X2. To me, that's the starting point of thinking about multicollinearity.
Yeah, and it's baked into our interpretation of the regression coefficients, right? When you say something like, for a 1 unit increase in x1, we expect whatever b change is in y, holding x2 constant, right? So it's the marginal contribution, it's the above and beyond that's going on here. Because we want to know not just what the two variables can do collectively, which we get in the multiple r squared, but then also we often want to know what each one can do above and beyond the other. And that was easy when they didn't overlap at all, because they did their own thing. In fact, the standardized regression coefficients in that world were the actual Pearson correlations that each of those variables had with y. But once there's overlap between x1 and x2, things start getting a little bit trickier.
I did my hand waving with circles because that's pretty much the extent of my knowledge about statistics. How does this manifest itself within geometry? Because that's where the real meat of the sandwich lies in multicollinearity.
Right, so here we go again, trying to give a highly visual explanation without any visual stuff here. All right, close your eyes.
No, not if you're driving. Keep your eyes open.
All right, well, I've got an x1, an x2, and y, and I'd like us to think about this in terms of the scatter plot that it forms. And that's a three-dimensional space, so it's like a box, and I'm going to dangle points in that particular box, and they're going to make a shape. And the shape that they make is going to be reflective of the relations that the variables themselves have. If it is a completely spherical shape, then that means x1 and x2 aren't related, and they're also not related to y. But if x1 and x2 are related to y, we start to get something that's a little bit more elongated, like an American football or a rugby ball, whatever you want to call it. And maybe even, we use this example in the context of principal components analysis, the flattened croissant that's been sitting on my counter for 10 days. Imagine that that is the scatter plot that we have. When we're doing multiple regression, what we're doing is we're fitting a plane through that. A plane that tilts a little bit depending on x1, tilts a little bit depending on x2, but in the end tries to maximize the explained variance in y. In other words, it tries to minimize how far the points are above and below that particular plane. That's the way I want to think about it for right now.
So the key to all of this is that one or more of our predictors, and in reality, all of our predictors correlate to some degree.
Mm-hmm.
The entire general linear model is based on these correlations, and these are fundamental to building an understanding about the complexities of life around us. But it can go wrong when those correlations start getting bigger and bigger and bigger.
They absolutely can. If I have some deflated football or flattened croissant that is my scatter plot in three-dimensional space, imagine that the floor of this space is defined by x1 and x2, and then y is the altitude of this space. Very standard way of kind of thinking about it. The relation of x1 and x2 would be the shadow of that scatter plot down there on the floor. And if x1 and x2 aren't related to each other at all, that shadow is just going to be a blob. Because I'm talking about the data having the shape of a football or a croissant, we actually expect the shadow down there on the floor, where x1 and x2 are, to be a little bit more elliptical. Well, let's keep turning that knob up of the relation between x1 and x2. Imagine instead of me having this flattened croissant as my scatter plot, imagine I have an Olive Garden breadstick or a baguette or something that is very, very long and skinny. The shadow, of course, is going to be this very, very long-looking thing that will show that x1 and x2 are related to each other. Now, if I tell you that you have this baguette in space... I don't know why that makes me... Baguettes in space.
Stay on task here, Hancock.
Sorry. Imagine I tell you to fit the best fit plane through a baguette or a breadstick. There's that sort of pause. When it was a flattened croissant, you would go, well, I would just put it right through the middle of that flat croissant. But if it's long, skinny breadstick where you have this tighter and tighter correlation between x1 and x2, I could fit the best fit plane horizontally or at a little angle this way, a little angle that way. you get a lot more instability in terms of where that best fit plane is going to go in order to fit that shape that reflects greater and greater collinearity between our two x's. And this is symbolic geometrically of the problems that we encounter as a result of multicollinearity.
So this puts us in a gray area. We almost require correlations among our set of predictors because it is validly reflecting the complexity of life as lived. But you can have too much of a good thing. As Greg is pointing out, as these correlations become higher and higher and higher, things start happening in the model. There's instability. The model becomes highly impacted by idiosyncratic characteristics of the data. Your standard errors start getting larger. This is where Kaiser Soze comes in.
A gift from Mr. Soze.
How many masters or dissertations have you been at where there's been a hypothesis about some predictor, and in the final model, that predictor, even though it had a bivariate correlation with the outcome, is not a significant, unique predictor? So the research hypothesis is not supported. The student, with some confidence, says, well, that's not truly reflective of evaluation of the theory. It's multicollinearity. That is
Kaiser Soze.
Okay, well, let's be concrete about what multicollinearity is, because right now we've only been talking about two predictors, x1 and x2. And so even though there are multiple variables involved in this, multicollinearity is a phenomenon that pertains to our predictors. And when we only have x1 and x2, there's not much multi about it. We just have one single correlation. And we can look at that correlation and go, oh, gee, that looks kind of high. Although I don't actually know what that means. Even for only two predictors, I don't know what that means, because even if you have a correlation of 0.7 between two of your predictors, what do we always tell our students in terms of explained variance?
square that baby.
That's right. Square your 0.7 or your minus 0.7, I don't care. And it means that those two variables don't even share half of their variance. So first thing, just to give yourself a little bit of perspective, is to think about things in terms of R-squareds. Not R-squareds with Y, though. R-squareds relating the predictors. Okay, so now let's extend that to having a bunch of variables, x1, x2, all the way to xp. Lots of opportunity for correlations among those, and we could certainly look at the bivariate correlations among them, and that might be informative to try to understand whether or not there are relations, but you could have some pretty meh bivariate correlations among a whole bunch of predictors and still have high multicollinearity. So then what do we mean in terms of multicollinearity? Here's the way I like to think about it. Imagine I take each predictor and I assess its degree of overlap with all of the other predictors collectively. In fact, forget about Y entirely for just a minute. I could take x1 and ask the question, how much does x1 overlap with x2 through xp? That's a multiple correlation, or a squared multiple correlation. I could do that for each of the predictors. How much does x2 overlap with all of the other predictors, including x1, and so forth and so forth. So I can get R-squareds that just relate each of those. Those are going to be telling us a little bit more about multicollinearity because it's taking all of the information into account. That's where you start picking up on a little bit more overlap.
So given your description, what does it mean to have, air quotes, multicollinearity?
Well, one way to think about it is in terms of the multiple R-squareds that just relate the predictors. True multicollinearity, I don't mean sneaking up on it, worrying about it, thinking about it. True multicollinearity means that at least one of those R-squareds is going to be 1, so that the information that is contained in a variable is completely redundant with information that is contained in one or more other variables. And this is all just among your predictors. That would be true multicollinearity.
So it's a little awkward, but the stump grinders accidentally uncovered both Gauss and Markov. And so while I was out there, I went ahead and dragged them in, and I've got them propped up in the corner. And they have a thing or two to say about all of this.
Okay.
Gauss-Markov theorem underlies the general linear model. We've talked about this on prior episodes. They have a condition in Gauss-Markov. It's paraphrased across different textbooks. There is no multicollinearity is a simplification of Gauss-Markov. Mm-hmm. What they mean in the strictest sense is that there is not the condition that you just described. that there is a perfect collinearity. I really like your description of regress each x on all other x's. And one of those r-squareds is 1.0. That's exactly what we're talking about. They set out that you cannot have that condition. Why? Because in the computation of the regression coefficients under ordinary least squares, part of that expression is x prime x, wait for it, inverse.
Oh, there it is.
All right, so x is your data matrix. Notice you alluded to something and you put it out there as kind of a teaser. You flirted with this notion that all of multicollinearity is model-free. Notice y is nowhere in here. This is a characteristic of your predictor variables.
That's right.
Your raw data matrix is x. X prime x gives you what's called a sums of squares and cross products matrix. To invert it, you need a determinant. To have a determinant greater than 0, you need to not have multicollinearity. So Gauss and Markov are brushing stump debris off of them and are grunting happily because the point of their theorem was you cannot have multicollinearity because you are unable to invert x prime x and you cannot calculate the OLS estimate.
Yeah, the concept of multicollinearity has experienced some creep over the years, right? In terms of Gauss-Markov, it means perfectly collinear, perfect multicollinearity. So why do we let the idea of some amount of overlap, an uncomfortable amount of overlap, why do we let that bother us in the stuff that we're doing?
It's all
Kaiser Soze.
because if you say you have multicollinearity in the strictest definition of the term, then you were not able to obtain estimates within OLS, or it extends to maximum likelihood because you got to invert stuff there as well. You don't have multicollinearity. You have a system of variables that overlap to the degree that it may be introducing problems into the estimation of the model. That is, we're approaching multicollinearity.
Just so happens that your friend here is only mostly dead. There's a big difference between mostly dead and all dead.
Have you ever visited Ireland?
I have visited Ireland.
Did you go to the Cliffs of Moher?
No, I went to the bars of Dublin.
So you did the primary thing that you were responsible.
Yeah.
For those of you who have ever been to the Cliffs of Moher, the most wonderful thing about it is there are absolutely no safety features at all. You can just walk right up and look over the edge. And what I love about it is you can sit back and it is a one-item personality test for an individual to watch each and every person, how close do they get to the edge of the cliff. There's some people that just walk right up and lean over and look down, and there are others that don't get out of their car in the parking lot. What we do is that edge of the cliff is multicollinearity. You go over it, you're done and done, right? Mm-hmm. You have a linear dependency, you have a zero determinant, you cannot invert x prime x, and you're finished. What we deal with in everyday life in our general linear model is how close to the edge of that cliff are we going to get? Rarely, if ever, do we have true multicollinearity. You don't have an r-squared for one of your x's as a function of all the other x's that is 1.0, but maybe it's 0.5 or 0.6 or 0.7. And we can start to wander closer to that cliff where things start happening.
First of all, how close did you get to the cliff? You probably sat there and dangled your feet over, didn't you?
There is a picture of me and the kids on our stomachs side by side looking over the edge of the cliff, and my wife almost divorced me for it.
Right.
But in fairness to me, she's the one who took the picture.
Get closer, sweetie. Get closer.
She's an enabler.
Well, so there are a lot of ways of measuring how close to that cliff you are. I mentioned r-squareds as one particular way, where it's the amount of shared variance between each predictor and all of the other predictors. Sometimes people will take 1 minus each of those r-squareds and call that each variable's tolerance. All right, 1 minus r-squared, potato, potato. That would mean that if there's an r-squared of 0.90 of one predictor with all of the other predictors, the tolerance would be 1 minus that, or 0.10. And as r-squared gets bigger, then tolerance gets smaller and smaller. Sometimes people will take the reciprocal of the tolerance, and that's something called the variance inflation factor. So if I had an R squared of 0.9, then I had a tolerance of 0.1. 1 over that would give me a variance inflation factor of 10. The reason it's called a variance inflation factor is because it tells you how much the variance of the estimate of that variable's slope will be inflated as a result of the collinearity that that variable has with all of the other predictors, right? So the variance of that is the squared standard error. So I have different ways of assessing it. Those aren't the only ones. Those are some of the most common ones. They're nice because they're variable specific. But I don't know when I should worry, right? How close to the cliff is so close? And is it so bad being close to the cliff anyway?
Exactly, because we're trying to model life as lived, and the bottom line is a lot of things that we study are correlated with one another. That is not necessarily a limitation or problem or error in the model. It's a reflection of our measures, our samples, and the constructs that we're studying. What Greg just described, and that was a really nice description, I thought, of the variance inflation factor, that is often considered another regression diagnostic. But still, we have these ridiculous, if it's less than 2, a variance inflation factor, there's not a problem. If it's 2 to 5, that's modest. If it's 5 to 10, you have, a moderate. And nobody knows. I mean, these are just numbers that we pull out of our butt and pretend like we know something about.
Yep.
What happens to the model when we start to approach the edge of that cliff? There are a handful of things that occur. First, although we may not have a determinant of 0, maybe we have a determinant very close to 0. So we're right at the edge of the cliff. Well, that's going to start to introduce numerical imprecision in the estimate of that inverse of x prime x, and we're going to have a highly unstable estimate. We get very large standard errors, and that's what Greg alluded to with the variance inflation factor, is to what extent are those variance estimates of the parameters being excessively inflated because of collinearity. You know what's really interesting? The model becomes highly sensitive to idiosyncratic characteristics of the data.
Yep.
When you have this instability, when you have the Olive Garden breadstick that your regression plane is sitting on, do you go ahead and take one observation and doink it a couple of times?
Yep.
Doink, doink, doink. Just move it down the number line a little bit. Your regression plane is balanced on this breadstick, and it's going to be much more susceptible to start to waver back and forth. So it's very idiosyncratic. And then because of all of these things, it undermines replicability. Right? If we were to replicate that experiment and the same conditions hold, we may get very different results because all of this stuff is dangling on a wing and a prayer.
It is, but I would say it should be.
Right. Yep. Notice I didn't make any value judgments.
That's right. So we can say, the problem is multicollinearity. Multicollinearity, even allowing the definition of multicollinearity to be this gray space where it has varying degrees of overlap, just because you have instability in your slope estimate doesn't make the slope biased. It just means it's very hard to trust the value that you got from that particular sample. And you look at the standard error around it, and the standard error is massive for exactly the reason Patrick is describing, that when you have the Olive Garden breadstick and you're trying to fit a plane in it, that plane is highly unstable. It should be a couple points and it goes a different way. That's exactly what should happen. So you get this instability, but that's appropriate for this particular world. If you have a lot of overlap, a variable should be difficult to determine its contribution above and beyond other things. It doesn't mean that the variables as a system are not helping you to understand why, but it means exactly what it should mean, that it's very hard to nail down the unique contribution. And to me, that is a result.
That's right. That's what you get. The system is doing what it should. Because what are hints or clues in your own model to indicate that you may have a high degree of overlap among your predictors? Well, there are two big ones. One is, at the extreme, you have a very large R squared. All right, so we're going to bring Y in now. Everything we've been talking about up till now has been with the X side on the multicollinearity. We're going to bring Y in. Let's say you have 10 predictors, and you are able to invert your matrix. You get your solution, and let's say you get a multiple R squared of 0.9. We never get those in the social sciences. I work with a buddy of mine in nanotech, and he gets R squareds of 0.999 and grouses about it. And I'm like, oh, dude, I'm happy with an R squared of 0.2. But let's say you get an R squared of 0.9, yet not one of your predictors has a unique effect above and beyond the other predictors. That's a classic condition in which you have a high degree of correlation among your predictors, is jointly they're explaining a very large percent of the variability in the dependent variable, but no one predictor accounts for unique variance above and beyond the other predictors. Like everything that we do, rarely, if ever, do we have that at that extreme. But what we do have is maybe a bivariate correlation between a key predictor that's near and dear to your heart and the outcome. Let's say that your whole master's is written around the prediction of alcohol use from anxiety, and alcohol use and anxiety have a bivariate correlation of 0.6. But when you bring it into the multiple regression and control for demographics and concurrent depression, anxiety is not a unique predictor of the outcome.
Is Kaiser Soze.
But here's the cold, hard truth. It's not. The reason anxiety is not a unique predictor is not because of multicollinearity.
Exactly. First of all, let me reiterate what I said before. That should be your result, right? We think that somehow we are painted into this embarrassing corner when, oh my gosh, none of my predictors are significant. But you've got that monster R squared over there. Congratulations, you have the right variables on the table. And any one of those variables' failure to distinguish itself above and beyond the others doesn't mean you have failed to understand what's going on as a system. So I don't consider that a failure. I consider that a result. That's thing one. I just needed to say that again. Thank you. Thing two is not all collinearity is even relevant for the things that you're doing. It might be the case that you consider, for example, X1 and X2 to be your really, really important predictors, and then X3, 4, 5, 6, etc. are all these variables that in your mind you think of as control variables or covariates. Knock yourself out. You can have a lot of collinearity among those control variables. That doesn't even matter. So when we're talking about multicollinearity here, we talk about it in this gestalt. But if it's happening among the variables that you consider to be control variables, that doesn't even affect the standard error associated with the prediction of the variable that you have there. So we really have to be a little bit more precise. It's also the case that you are often the reason for the multicollinearity. If you, for example, are trying to look at nonlinear relations, so you've got X as a predictor and you've got X squared as a predictor, well, congratulations, there's usually overlap between X and X squared. And don't fool yourself into thinking that centering is somehow going to magically change everything in the world. We had a whole episode about centering. You might have X1 and X2 and the product between X1 and X2 because you're interested in moderating or interactive kinds of relations. Well, guess what? You're building another predictor out of other predictors. You are baking collinearity into the system, and that's okay. That's appropriate for the thing that you are studying. What if you are looking at the predictive value of some time 2 variable, but you want to control for what was going on at time 1? Well, maybe the contribution of time 2 above and beyond time 1 is negligible. It should be negligible. Those variables covary with each other. So I just really want to emphasize that the things that we're talking about observing as a result of multicollinearity are things that you should be observing. Multicollinearity isn't to blame. It's just the conditions under which the phenomena you are studying exist.
There is no Kaiser Soze.
One that I often see is poor measurement. And I don't mean poor in the sense of bad items or poorly scored manifest variables, but that there is not sufficient conceptual distinction between subconstructs that would support them being individual predictors. Mm-hmm. We've talked a lot across a lot of episodes about measurement and factor models and common factors. I've seen many situations where there have been 3 or 4 predictors where the student has ostensibly been, and I'm going to use air quotes, interested in the unique effect of each predictor above and beyond the others. But my common question for them is, looking at your theory and looking at the items, shouldn't those 4 measures be indicators on a single underlying construct? So the whole foundation of factor analysis is that the reason a set of items are correlated with one another is because they share a common cause.
Right.
And when you estimate and remove that common cause, those correlations among the items go to 0. That literally is factor analysis.
Yeah.
And so if you have 4 dimensions of social support, and you're vexed that you don't get unique prediction of each above and beyond the other, congratulations, you invented factor analysis. Maybe they shouldn't be 4 independent items. Maybe you should create a scale of those. So part of it is measurement, potentially, where this high degree of correlation comes from. Part of it might be sampling. Maybe your sample is constructed in a way where some sub-portion of that sample is correlated with other things in your predictor. And when you estimate and remove differences in the outcome as a function of a demographic variable, there's nothing left over. Because it opened its suitcase, took everything it knew about alcohol use and left, because that is somehow correlated with some demographic variable, and there just ain't nothing left. So you got measurement, you got sampling. The one I very often come back to is, yeah, that's how things behave in the world. Right? Is a lot of work I do, both in my own stuff and in student committees and things like that, is a focus on things like depression, anxiety, and social withdrawal in the prediction of some outcome. All right, that's a great research question. How do depression, anxiety, and social withdrawal jointly predict substance use in adolescence? And maybe we get some reasonable R-squared. You get 0.25. The optimal linear combination of depression, anxiety, and social withdrawal accounts for 25% of the observed variability in alcohol use. Yet not one is a unique predictor above and beyond the other 2. And people pull their hair and say, oh my gosh, my theory is undermined. Why don't I get this? Well, it's the joint contribution that is supporting your theory. And what it's saying is, when you account for everything you know about anxiety and depression, there ain't nothing left for social withdrawal to account for on its own.
That's right.
And so that's not bad measurement. That's not bad sampling. That's not some Kaiser-Soze characteristic of the model. That is just simply you're working at levels of subtlety that you're not able to isolate that unique effect given the other information you have about the individual as they live their lives.
And use the word prediction in there. And I really want to underscore that you might have a lot of overlap among your predictors by any measure, variance inflation factor, tolerance, individual predictor R-squareds, whatever you want to think about. You've got some high degree of this stuff. You are close to the cliff, or at least your kids are. You're sort of urging them. So you've got all of that going on. And we talk about the impact that that can have on the standard errors, the impact it can have on the stability of the estimate of those individual slopes. But it doesn't have to mess with your predictions, right? So if you think about that breadstick, we talked about putting in the best fit plane can be highly unstable. First of all, where does it go? Second of all, a couple of points here, a couple of points there, and that thing radically shifts. But you know what? It's still a long, skinny breadstick. And that means that if I know your X1 and I know your X2, then I have a really good chance of getting your Y really, really close. And the error around that is not very big, right? Because the breadstick is a very long, skinny thing. So we have to be careful not to confuse the inability to find a significant contribution of one variable above and beyond the others with meaning our system isn't doing a good job, because our system might be doing a good job, and to think that it means we can't make good predictions. You can make outstanding predictions in the face of high degrees of collinearity. And that's often your goal. Often your goal is to come up with some sort of diagnosis, some sort of really tightly bounded prediction, and you can still do that.
Do not blame Kaiser-Soze. More often than not, the reason that you did not find a unique effect associated with anxiety above and beyond all other predictors in your model is not Kaiser-Soze. It's not multicollinearity. It is not something that you can say, well, I would have found support for my theory if I didn't have multicollinearity. First, from a strict perspective, that is not multicollinearity. You were able to invert your matrix, you got a solution, you don't have multicollinearity. That doesn't mean you can't be approaching that. It doesn't mean that you can't have a lot of overlap, but unless there's an error in your measurement, an error in your data management, as Greg has said a couple of times, this is an accurate reflection of your measuring your samples. If you have a correlation of 0.7 between two variables, and keep in mind that's still not even 50% of the overlapping variance, this is a reflection of your data space. And the last thing that I have to say is what you've said a couple of times and just reiterating, I feel like as a field, we need to do a better job of not putting all of our emphasis on the unique effects.
Right.
I'm not saying those are not important. I am not saying that those don't play a critical role. But how many projects I've been on where there's been a multiple R squared from the system of variables of 0.3 or 0.4 or 0.5, which is very strong prediction in our field of study, and one or two predictors were not significant in a unique perspective, and the entire project was deemed a failure.
Yeah.
I think we excessively focus on unique effects to our own detriment.
So people talk a lot about correcting for it, doing things about it. You know, sometimes people will say, oh, collapse the variables and make a single score out of them, or use a principal component analysis, or toss one of the variables out, or use lasso or ridge regression to try to get around that particular problem. I think the best thing to do to deal with multicollinearity is just stop being a whiny-ass baby about it. There's nothing to see here. Can we say that?
That's the point of the entire episode. It's not Kaiser Soze. This episode could have been a lot shorter if we just opened with that. You cannot blame your lack of support for your hypothesis on multicollinearity. It is not a technical characteristic or flaw of the model that has led to lack of support for your theoretical hypotheses. That is not to say you do not have overlap among your predictors, that there's not redundancy, that there may be issues in sampling, that your model may be sensitive to idiosyncratic characteristics of the data. Simply realize that this is the gig. Right? This is the game that we're in, is we're trying to get an optimal linear combination of a set of correlated predictors that maximizes the relation between that combination and the outcome that we've measured, and that this is just part of the price of playing that game.
So stop being say it with me,
Whiny ass baby.
All right. Thanks very much, everybody.
Yep. I'm going to go look at the hole in the ground where my stump used to be.
All right.
Bye-bye.
Bye.
And like that, he's gone.
Thank you so much for listening. You can subscribe to Quantitude on Apple Podcasts, Spotify, or wherever you get your audio files to help you go to sleep at night, and please leave us a review. You can also follow us on Twitter, or X, or whatever the hell it is now. We are @QuantitudePod. And check out our webpage at quantitudepod.org for searchable archives, playlists, show notes, and a brand new syllabus that organizes episodes under class topics. Finally, you can get non-pumpkin spice Quantitude theme merch at redbubble.com, where all proceeds from non-bootleg authorized products go to donors choose to support low-income schools. You have been listening to Quantitude, where after 4 years of trying to reach the edge of the cliff of quality, we still never quite get there. Quantitude has been brought to you by the Olive Garden. Who knew that in addition to contributing to a myriad of health problems, our all-you-can-eat breadsticks enhances the understanding of high-dimensional Euclidean geometry? By the all-new Quantitude scapegoating service. Do you encounter unexpected or inexplicable research results for which you do not want to take personal responsibility? For a small fee, we will officially license you to say, our theory would have been supported had it not been for Quantitude. People have been doing this for years, we're just trying to make some scratch off of it. And by the Cliffs of Moher. We have no personal safety features because we are not a country of whiny-ass babies. This is most definitely not NPR.